I've been always very curious about the low-level direct communication protocols between GPUs, especially if you're training large models in a large cluster of GPUs. You really depend on these protocols to squeeze out the best last optimizations for data transfer during training. So huge amount of efficiency really depends on them. So I never got good clarity on these and what are the bottlenecks, what are the challenges where they're stuck until I found this article by LeQuin Chen, who's in the Perplexity team right now. He talks. They've introduced a new RDMA communication library based on the idea of unordered, reliable datagram, and he goes into why they built this library, the motivation behind it, and what's the state of RDMA communication, which is the key form of communication among GPUs belonging to different nodes in a cluster, not on the same machine. On the same machine, you use something called NVlink to communicate between uh, NVIDIA chips, NVIDIA cards among on the same cluster on the same machine. But RDMA is RDMA based protocols are key to doing efficient transfer between different machines. So yeah, so they looked at a bunch of uh, RDMA based libraries, including DeepEP and then several others, and yeah, so the couple of options. RDMA protocols could be implemented in a collective format or a peer-to-peer format. Now, data parallelism, tensor parallelism, all those operators which are key use the collective structured parallelism. Uh, Several tensors are padded so that they fit into the single shape, static shape, and then they are um, sent over the network. So that is a compromise when it comes to stuff like KV cache sending, where or MOEs, mixture of experts, where every node wants to send a, a different uh, packet size to the other node, and collecting them together into a single shape is quite wasteful. So they say that each rank sends a variable number of tokens to every other rank. With collectives, you must size everything for the worst case, which can be 64x larger than the average, which is completely wasteful. So that motivates why you need RDMA P2P, and so they then double down into what are there any simple, easy to use RDMA library. Essentially, by simple, they mean that I think they mean that a good high level abstraction is missing, which can generalize across not just the Connectx NICs that are attached to um, NVIDIA GPUs, but also on other cloud interfaces like AWS. Okay, so underlying protocol is NCCL, but uh, which is common across NVIDIA chips, but these libraries work on the top of NCCL and have different assumptions about how the data is being transferred, and that's where the problem occurs. So what happens is they found that there's no simple, well abstracted out RDMA library. AWS has an NCCL plugin which lets NCCL run on EFA, which is their own protocol on AWS, which allows communication between different GPU nodes. But being able to run NCCL doesn't mean you can run other communication libraries because of several reasons. These are what makes RDMA code so hard to port. One of the fundamental bottlenecks is the ordering, the protocol level ordering. Many of these libraries assume that data packets would reach in an ordered manner. They'll reach in the same order as when they were transmitted, which is not true. And so if that is baked into one library DeepEP implementation, it's very hard to get rid of it. Then the NIC bandwidth differs. EFA is 100 Gbps, Connectx can do 400 Gbps, so you need multiple EFAs to match single connectors. And then the features differ. Only Connectx supports what is called IBGDA, and you need CPU mediation and so on. And then there is that stuff, non-portable interfaces. NVS HMM is one of them. So yeah, so these problems make it difficult to make a portable RDMA library across NICs. So there's a very nice journey into the crux of the problem. And so once they discovered it, they approach the problem and build a library which has its own unique assumptions, which as they explain later, this library is quite general and works on both local cluster as well as on AWS, and works across KV cache, RL weight updates, and MOE communication, which are different forms of cross GPU. These modules involved different kind of cross GPU communication. Here's again the key aspect: reliable delivery. If packets transmitted must be received. Unordered deliveries where embrace the hardware reality and don't force the ordering. And the high-level protocol takes care of it. Bunch of other things: two-sided send receive, one-sided write im, Zim counter, high-level optimized interfaces for common patterns like multi-page write or multi-receiver write, and then aggregation, which is split by byte ranges, or pageless or receiver. These are all low-level primitives that are used in these protocols, and the library accommodates all of these to build a more universal, let's say, RDMA library. Okay, so by having this assumption, and there's a very nice thing called host proxy GPU RDMA, which they go into more detail in the MOE kernel story. Yeah, so having their own assumption doesn't preserve compatibility, but I think it's a new layer of abstraction that they have come up with, and they've thought through it deeply. So it should be far more generalizable, far more usable by new teams. Okay, and the good thing is that they wanted to optimize just for KV cache transfer protocols, but it works for RL updates and then for MOE communication too. So he goes more deep into the MOE kernel story and how they started with trying to port DeepEP to EFA. And to get the best results, you may need to design kernel of unordered delivery day one. That's when they realized that ordered delivery was one of the key assumptions that prevented DeepEP from porting. Okay, and the very nice low-level story here, and sort of coming of age story here, and they led to a bunch of optimizations, and they've documented in the paper RDMA point-to-point LLM systems, and there come a bunch of perplexity blog posts. So the essence being that the bunch of low-level RDMA semantics which were assumed by libraries, made it difficult to port it from Connectx to EFA, and by thinking through, they managed to create a more general, higher-level abstraction library which ports to EFA and is equi-performant, if not better in some cases. So this really highlights what goes into optimizing low-level communication protocols among NVIDIA cards, something for which the information is really low, and it's the first time I've come across such a detailed article on the topic. And also to highlight that it's not always about optimizing CUDA kernel for example, attention layer or something. it's a full stack optimization. When you're doing large scale cluster training, it's really important to optimize these low level communication protocols across the GPUs.